Jai Hind everyone. I am Dr. B. N. Pandey from Ajay Kumar Garg Engineering College. We are taking lectures on the complex topic, and in this sequence today I am taking the content which I have already given in one lecture, Lexical Analyzer, and in that lecture I have just explained that how Lexical Analyzer is worked, what are requirements for Lexical Analyzer, because it takes input, source program as input, and given tokens, which is meaningful sequences or computational part of the program, which is just converted into the finally machine code by using the whole process of compilation. In previous lecture, I have talked about how the Lexical Analyzer work, what are Lex compilers, what are auxiliary definitions, translation rules, how you can just convert a source program into sequence of tokens. But in this lecture, I am just briefly covered how to describe tokens, how to specify tokens. Then because regular grammar and transition diagram is the specific part through which you can just generate these tokens, because it's very effective process or effective methodology to describe tokens. So we are discussing transition diagram, and we're just giving some examples of different tokens through this, how we can interpret through transition diagram. Then what is Lexical Analyzer generator, and the last part is some other issues in Lexical Analyzer. How to describe tokens. So how you will describe the tokens from a given source program. So programming language tokens can be described by regular language. What we are using, the finite automata is required to describe the tokens, the regular languages, which is accepted by different regular grammars. So what are regular languages? That because why we are taking regular languages to describe tokens, because they have some particular characteristics. One is it is easy to understand. There is a well understood and useful theory. They have efficient implementation. Means things are very stable and very definite if you are using regular languages, because you all are aware that the finite automata, why we call it finite automata, because for every particular accepted language, it generates a specific machine. So it's the power of regular grammar. That's why we are using this for describing tokens, because every token has their unique meaning and we must derive that token from the source language. So regular languages has been discussed in great detail in the theory of computation course. We have already talked about in finite automata theory subject. Here we are using some part of that, but definitely DFA, NFA, anonymization, because when we are going to generate a lexical analyzer, the whole process is just, firstly you have to find out the regular expression which is accepted language, that is called regular language, basically, which is accepted by or just generated the particular token. Then we have to generate a epsilon NFA with epsilon for that. Then generate the DFA by subset construction algo, then minimize the DFA, and then we are getting the particular lexical analyzer through which we can give the input as a source program, and we are getting the tokens. How to specify tokens? So regular definitions are used. That is basically called auxiliary definition or regular definition. That is one minute. Auxiliary definition or regular definition. That is called, this one is auxiliary definition. Okay, or we are called regular definition, and it is derived by some name derived by regular expression. So when we are going to specify a token, means a specification of tokens means in which category it is lying, its value is unique, or we have just a lot of values where we can install like identifier. We don't have a single value every time we have to install the identifier because it is variable. Then constant, it has a lot of values. But if you're talking about keyword, it is unique. So RIB, regular expression that derives the particular token, and DIB, the distinct name. So regular definition is a sequence of definition of the form where each regular expression is the expression. So RI belongs to summation union or distinct name, union all distinct name D1, D2 and up to Okay, if you're taking example, so we have to take example like if you are using for identifier, if we are using for identifier, if you are using letter by digit closer, then you see that letter and digit is the name. But still, what is the regular definition? What are the regular expression involved in that? So if you are deriving the letter, so letter is a distinct name, that is basically D1. And what is R1? A capital A, B, C / small a, B, C up to Z. If you're talking about digit, then it is 0, 1 up to 9. So that is the basically regular definition through which we can specify the tokens. Like examples, if you are taking my fax number, so it is combination of digits, that's 91512259758, summation equals to, if you are taking summation digit union minus plus minus left parenthesis right parenthesis. If you are representing country, it is digit plus digit square, area equals to digit plus exchange equals to digit phone, digit plus number. So these are the basically examples of regular definitions. Some distinct name is there and it is derived by some particular regular expression. You will see that at right hand side, you will see that everything is a regular expression. Like my email address, where summation equals to this, letter name I have already given, address name @ name dot something something. So these are the basically regular definitions. Identifier we can define, unsigned number in C. So a lot of examples are there, you will see that. What is the purpose? Why this regular definition is required? If you are taking direct values, like suppose a regular expression is like that. So this is the part of summation of AB. So here there is no regular definition because every terminal is directly derived, that is string. Okay. But I have already given the example. Suppose if you are talking about constant. Okay. And we are using the regular expression that is called digit closer. Okay. So this digit is not directly is a part of summation. So what you have to do? You have to just derive it by regular expression, though I have already explained that. And that is given in the form of digit. You will see here, it is given in the form of digit. Identifier is given by letter by digit closer. So these all are regular expression. Like unsigned number of C, means these are the basically examples of your tokens, and these tokens are specified by some regular definitions that is basically conveyed here. Now, how we are using regular expression in specification? The important thing why we are using regular expression, because the finite automata is very important tool, very specific tool through which we can easily recognize or specify the tokens, because every token has unique value, and whatever machine we require through which we can separate all the tokens. Okay, and every token has their meaning in the program. So regular expressions describe many useful languages. The important thing, the first one is regular expressions are only specification, implementation is still required, because regular expression is not a complete value. It is accepted language up for that, but what language it is accepted, you have to implement when you derive the transition diagram. When you derive the DFA, then only the machine will be built. So it is only the specification, it is not implementation. Given a string S and small a, regular expression R, does S belong to LR? Okay, if any string is given and a regular expression is given, so we will check that string belongs to regular expression or not. If it is belongs to regular expression or, definitely it is a part of that regular expression, you can derive the token. Otherwise it is not the part of that. Solution to this problem is the basis of the lexical analyzer. If you are finding out different tokens, derive a regular expression for those tokens. And if every token is the part of that regular expression, then that is generalized regular expression for the all tokens. But every token is unique. If you're talking about keyword, it is for, if, while, these all are keyword in C. Okay, if you're talking about identifier, then it is A, B, C, and any other. If you're talking about constant, then 0, 1, 1, 2, 3, 2, 3, 2, these are the constant. If we're talking about the operator, then equals to, plus, less than, equals to, these are the operators. So important thing, how we will specify the tokens by using regular expression. It's very important matter, and through that we will generate the concept for lexical analyzer generator, because we are using that lexical analyzer generator to generate lexical analyzer through some source program, some particular specific programming construct, and we are getting the particular lexical analyzer through which we can take source program as input, and we can separate all these tokens using that machine. However, just the yes no answer is not sufficient. We need some model. We need to derive a particular specific partial program for that, so that we will find that what is the functionality of lexical analyzer. Goal, partition the input into tokens. The important thing, if we have a source program, initially identify the tokens, then we have to make a program, or we have to make a model, we have to make a lexical analyzer through which we can separate all the tokens, because in source program it is a bunch of tokens. So write a regulation for lexemes of each token. So here three terms are there. We have already talked about that. Token, lexeme, and pattern. This is generalized regular expression, RE. This is basically a particular part which have two attributes. A pair of attributes, it has token name and token ID. And lexeme is the exact value of this regular expression. For example, if you're talking about constant, so the pattern for constant is digit closure. But you are talking about lexeme, 0 is a lexeme, 232 is a lexeme. Okay. And if you're talking about token, so it is a constant type of token. So these are the representation. So write a regular expression for lexemes of each token. Like if you're representing the number, it is derived by digit plus, because 0 is not considered as that. Plus means it would not take empty string. 0 is okay, but empty string it would not. Then for identifier, letter by digit plus. We can use here closure also. Then construct R matching all lexemes of all tokens. Whatever tokens we have already derived, what we have to derive a regular expression which matching all lexemes of them. All lexemes of different tokens. So whatever combination we will take, the particular regular expression will cover all, will just cover all the tokens. It will not left any of the token of the given program. Let input be x1, 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 x2 up to xn. For 1 is less or equals to n. Suppose n number of regular expressions are required. Then we have to generate it which belongs to that set of regular expression. So if you are taking smallest such j is token class of x1, remove x1, xi from input go to 3. Important thing, what you have to do, you have to derive the regular expression in terms of the chunks, because different regular expressions are there and different tokens are there. For every token, you will derive a set of tokens. Then you will check that it will cover all the tokens or not. If it is not cover all the tokens, then again you have to change the input, and this process is going on. The algorithm gives priority to tokens listed earlier, treats if as keyword and not identifier. Okay. Suppose if you are talking about how much input is used, what if you are using x1, xi, x1, xj, pick up the longest possible string and LR, the principle of maximal munch. So regular expression provide a concise and useful notation for string patterns. Good algorithm require a single pass over the input. So important thing, because if you're talking about identifier, like you are talking about identifier, but you know that the particular keywords are also collection of alphabets. So it's a just a overlapping part, because sometime it is keyword, sometime it is identifier. Okay, so you have to take in care that if keyword is matching, then definitely we have to design a machine, we have to design a regular expression set through that the particular keyword has been identified, because it is just stored in library function, and symbol table is also used for that, and all the information is available in symbol table. So we have to go for symbol table and check that, okay, it is keyword or identifier. If it is keyword, then it is a library function, but if it is not keyword, then you can say that identifier. So all combination, why this algorithm is given, because we can just build a one machine through which we can take as input a source program, and that machine will separate all kinds of tokens. So this is the base benefit for the regular expressions. How to break up next? So we are using input buffering, and then like here one program is given, else x equals to 0. Regular expression are not enough, okay, because regular expression is required, but we have to require some memory requirement are also. So here input buffering is required, so that we will traverse this one by one. Normally the longest match will win. Ties are resolved by prioritizing tokens. Lexical definition consists of regular definitions, priority rules, and maximal munch principle. Now we are talking about transition diagram. So transition diagram, if you are talking, so regular expression are declarative specification. Transition diagram is as an implementation. Earlier I have said that at that time when we are converting this into, and the whole process is there. What we are doing? We have to start with regular expression. Then we are using Thompson construction algorithm. Okay. We are generating epsilon and fa. Then we are using subset construction algo. That is called epsilon closure method. We generate DFA. Then minimize this DFA. And what transition diagram we are getting, that is basically your lexical analyzer generator. So transition diagram is an implementation. A transition diagram consists of an input alphabet belonging to summation, a set of state, a set of transition state, a set of final. These are DFA. Transition S1 to AS2 is reached. So that is basically the transition will be so Q comma A or what. So next state go to. So this is the transition diagram. So this is the state, final state. These are the notations. Transition from state I to state J on input A. How to recognize tokens? Okay, how to? Suppose relational operators. So this is one particular chunk will be given, so that we will identify the tokens. Like if you're talking about relational operator, it will contain these operators, then ID, then number, then delimiter, and then white spaces. Okay. So what we do, construct an analyzer that will return token per attribute pairs. So we will draw that. So this is the transition diagram for a relational operator. So equals to, then greater or equals to, okay, greater or equals to, then equals to, then less than, greater than, less than, equals to. So these are the separate diagrams for the, so you will say that it is regular expression for that particular token. So for greater or equals to, this final state will derive, greater than this final state will derive, less than this final state will derive. So these are different basically lexemes, means it is tokens, which we will make a combined diagram through which we can take such kind of input and we are deriving the strings. So transition diagram for identifier, white spaces, all separate transition diagrams have been given. This is transition diagrams for unsigned number, real number, integer number, all other combinations has been given. The lexeme for a given token must be the longest possible. Assume input to be 112.34 e to the power 5, 6. Starting in the third, diagram, the except state will be reached after 12. Therefore, the matching should always start with the first transition diagram. If failure occurs in one transition diagram, then retract the forward pointer to the start state and activate the next diagram. If failure occurs in all diagrams, then a lexical error has been occurred. So errors also. So implementation of transition diagram. How we can implement that? So token next taken. Which one is the next token? While one, switch a state because lot of tokens are there. So case 10 is given, C equals to next char, because case 10 is what? It is for basically for identifier. Okay. So this particular case is for identifier. Okay. Lot of cases are there. Suppose we are just deriving relational operator, then we are using for program that. So case 10, firstly you have to take C character because we are deriving the character in, if you are using this transition diagram. So this transition diagram is what? Letter, then letter by digit closer. Okay. Then final state here delimiter you can use. Okay. So this is the diagram. So for this transition diagram, how implementation is done? C equals to next char. We are using two functions, is letter and is digit. Is letter is what? Is identify the letter. Is digit is what? Is identify the. If is letter, because for first state, if you want to reach to second state, definitely the first input will be letter. Okay. So first condition, if is letter C, suppose there is a letter, then state equals to 10, because that state nomination is there. That could be 10. That would be 10, that would be 9, and that would be 11. We will see that. Okay. Else if is digit C, state equals to 10. Suppose if is digit, because letter and digit both. If is letter, then state 10. Again, if is letter is there, then else if letter by digit, is digit state 10. Else state 11. If we are not getting letter and letter digit on this particular state, then we have to move on the final state, because after that either white space are there or any kind of delimiter or semicolon, anything is there. If we are getting something different from letter and digit, what we have to do? We have to move the state 11, and state 11 is the final state for a particular identifier. So we will getting the identifier. So switch state means for which final state you want to draw that. Okay. So this is the basically implementation. This is unsigned number. That also example you will just write for every particular, you will write the program for every particular states given, like a state 0, 1, 2, 3, 4, whatever nomination is there. So we will use same. What is the lexical analyzer generator? Input to the generator, list of regular expression in priority order, associated action for each regular expression. So we have to associate action because some memory trigger is there. Suppose you are getting some keyword like for, some memory value, some token name is there. So 1 is written, 2 is written, 4 is written, 5, whatever memory conventions are applied. Then output of the generator is program that reads input character stream and breaks that into tokens, then reports lexical error. So this is these two works are important. If you are talking about lex, token specification, then lex is used, lex.yyc, C code for lexical analyzer. So when you are getting this code for everyone, lex.yy.c, then it is generated the lexical analyzer. Then you have to use the C compiler, object code is there. Then final lexical analyzer has been generated. So in here you will given the source program as input and you will be getting the tokens. How does less work? It is very important. Regular expression describes the languages that can be recognized by finite automata. We have already studied. Translate each token regular expression into a non-deterministic finite automata initially. So this is the process. Firstly, NFA you have to generate by using Thompson construction algo. Then DFA you have to generate by using subset construction algo. Then minimize the DFA to reduce the number of state. Whatever DFA, finally you are getting the DFA table. That is basically your final lexical analyzer, and Lex will work for that. It is called Lex compiler. Some other issues in Lexical Analyzer. This is last topic. One important thing is skipping comments. Normally we do not return a comment as a token. Okay, we skip a comment and return the next token, which is not a comment to the parser. So the comments are only processed by the Lexical Analyzer and do not complicate the syntax of the language. So it does not further proceed for the next particular phase. Symbol table interface, because every time we have to generate some token, and token information will be stored in that. And sometime in case of identifier, because the library functions is stored on the symbol table, but in case of identifier or any new value, definitely we have to check in the symbol table. If it is already there, no problem. If it is not already there, we have to just derive that, and the position of the tokens in the file for the error handling. Okay, so these are the complete part. Thank you very much. In next lecture, we will try to just start with the syntax analyzer. Thank you.